lines. Okay. Okay. So cohomology was all about the exterior derivative operator. Right? Homology is all about this operator we studied last time for the boundary operator. Mind you, the boundary operator was mapped D that took you from space of P chains to space of P minus 1 chains. Okay, and I'll show you how we can construct the boundary given a triangulation of a particular surface. So it doesn't take too much to twist you on to see that actually I can construct a sequence of these things. Right? That looks a little bit like this. And I'm going to label this guy by the chain space that it acts on. So D plus 1 takes you from the state of P plus 1 chain to the state of P chain, and then back to TP on this. I get to P minus 1, P minus 1 will take me to minus 2 chains. This goes on. And the point here is that the sequence of space, the sequence that I construct here is what's called a chain complex. And it is a finite sequence. And it is a finite sequence with the dimension of P being 0 if P is less than 0 greater than D. Okay. So chain complex is finite and the dimension CP is 0 if P is less than 0 or P is greater than the dimension of manifold. There are two important linear subspaces of each of the CPs that deserve mention in the same way that there were for the space of forms. So in a given chain complex, we distinguish in a given chain complex. Distinguish two spaces. One is the space of P cycles. Space of P cycle ZP is the set of all P chains there such that the P Z vanishes. Okay. This would like closed forms. And there are P boundaries BP which consists of a set of P chains B such that B can be written as D P plus 1 C, where C is some P plus 1 chain. Again, none of this should be conceptually difficult to understand. It's exactly what we were doing with closed forms and exact forms in cohomologies. And then, as usual, it's the fact that the boundary operator is not positive. That is, E squared is 0, boundaries don't have boundaries. Means that the set of boundaries is a subset of the set of cycles. In other words, all boundaries, any boundary is a cycle. The real question becomes, when is a cycle a boundary? So any boundary is a cycle. Spin is a cycle, also a boundary is this is obviously a non-trivial question. It's as non-trivial as asking when was an exact form closed. That's right, when is a closed form exact. But as in the other case, we'll be able to make some to do that. We can find the quotient space HP. What we did with the homology space in the labeling, P will upstairs, or homology will be downstairs. So they will. And this will be ZP on P. And this defines for us P homology space, depending on what we're defining it over, defining over the reals. It's a vector space, we're defining over the integer, that's module. But in either way, carry the group structure with it. So this is the P. Homology space. This is what we're going to study to try and answer this question. So the elements of this space consist of the set of equivalence classes of P cycles. And that's how we construct open space. So this consists of equivalence classes of P cycles where I will call two P cycles equivalent or homologous if they differ by a boundary. Where there's one and says two are homologous. Equivalent if Z1 minus Z2 is D of something. W. Well, let's say this is one, you can see. We'll denote the equivalence class of P cycles homologous to P cycle Z by square bracket. This is standard terminology. In that context. Okay. There's an important point to note here. If we take a step back, we started off with some differential manifold, and we associated to this differential manifold some tessellation, some triangulation of the manifold, right? And then we did some counting on this triangulation to determine what the chains were, what the cycles were, and what the boundaries were. So the chains, the cycles, the boundaries all depend on the spatial complex that I choose to triangulate my manifold. The important thing is that this guy does not. It depends only on the manifold. And the additional structure that comes from defining this over the reals or of the integers or whatever field you want to, or ring you want to define. Okay. So this is an important point. What it means is that somewhere in this falling out structure, the spatial complex that I use to tessellate the manifold gets worked out. Okay. So this is important because, for example, if I count the dimension of the space, right, and I construct things from the dimension of the space, they will define the topological quantities, topological invariants. Okay. Whereas really what goes into the construction depends on how you choose to tessellate your space. So for example, you can solve a two-sphere and you can choose to tessellate a two-sphere into a cube or a tetrahedron. You get different answers for boundaries and subsets and facility, okay, and the boundaries and the cycles. Okay. But the homology then you can start will be independent of that tessellation. Okay. In particular, one such topological invariant is something called the Betti number. The Betti number, let me make a note of what I just said. So while CP, Betti, and EP all depend on the triangulation or precisely spatial complex. That we triangulate everywhere. HP only depends on N. So what we might label, we might choose to label the chain space, the cycle space, the boundary space by the spatial complex that we're tessellating, that we're triangulating the manifold with. Right. This guy, the homology group, we will choose to only label by M and perhaps the thing that we're defining the robot. So we will write into P M maybe R or HP and I'll do a couple of examples with both of these and start it again.
When you say HP only depends on M, HP will look like other than HP. So we basically just say that the dimension of HP is independent because then.
Definitely. Yeah. So if you remember, it's, you know, depending on, for example, how many pages I have, it's just the dimension of the of CPU chain, right? That gets washed out in the quotient. So something that's going to be useful just now is the dimension of page P is called the piece better than that. So BP is the dimension of page P of M of N. So, just by way of anecdotes, when I was a student, there was a huge amount of development going on in essentially algebraic geometry and algebraic topology and differential geometry, and really the algebraic nature of this was important. And this development came from string theory. It was developments in pure mathematics preceded by ideas from string theory. And the ideas from string theory came in the following way. So there's a special class of manifolds, which we haven't talked about, we haven't had time to talk about. But if anybody interested, I'll give you notes later. Called Calabi-Yau manifolds. So these are even dimensional complex manifolds. So far everything that we've talked about are real manifolds. The quantization of those manifolds are real spaces, which you can imagine that you can take even dimensional such spaces, combine x's and y's into complex numbers, and that will define for you some complex spaces. But actually, a complex that by itself doesn't do it. You need additional structure. That additional structure allows you space with basically the manifold equivalent of the square root of -1. Okay, so there's an additional quantity that you can define, whose square is minus the identity, and that generalizes the idea of I for you. This allows you space for what's called complex structure. So there's a space that was projected to exist by Calabi with an even dimensional space with a certain structure, and then Yau came along and showed that you could get these Calabi-Yau manifolds by imposing a certain constraint on the curvature of this manifold, right? And you reach flat. That is, again, we haven't spent any time talking about geometry really in this differential geometry course. We've been going in the direction of algebraic topology and differential topology, right? But I can define, and if you've done any general relativity, you can define curvature invariance associated to the metric. So you take metric, take its derivative, you take combination of the derivative. That defines for you rank 4 tensors. You take the interior products, in other words, contracting indices. That defines for you rank 2 tensors. You take another interior product that defines for you a scalar. That scalar is what's called curvature tensor, and it's a curvature invariant. It's a differential. It satisfies the differential equation. That differential equation is Einstein's equation for general relativity. Well, Yau said, so Calabi comes along and gives a constraint on this, on what constitutes this Calabi-Yau type manifold. Yau comes along and says, well, back then I guess we should call Calabi manifold. Yau comes along and says, actually, that's equivalent to this manifold being Ricci flat. So now you just have to go look for all of these complex manifolds that are Ricci flat, and that proves Calabi's conjecture. And it turns out that in a seminal paper in the 1980s, Orwell, Vangelis, and Whitman show that in string theory was, this 10-dimensional theory, you needed to produce 4 dimensions that we live in. That gave you 6 dimensions to get rid of. So you had to compactify 6 of those dimensions. And it turns out that if you compactify them on a specific type of manifold, manifold, then you could get physics in the 4 dimensions looking like the physics that we experience today in the center world. Right? So these Calabi-Yau manifolds became all the rage in string theory. And string theorists, got very interested in these kinds of manifolds and studied the hell out of them. One of my PhD advisors was Philip Candelas, and he got famous for discovering something called mirror symmetry. So it turns out that you could calculate the homology groups associated to these manifolds. So these would be, M would be some even dimensional complex manifold, a Calabi-Yau manifold in particular. So you wouldn't be defining it over C, you'd be defining it over R. Sorry, not over R over C. And then you've got to calculate the homology groups, and you would calculate the Betti numbers, right? And these Betti numbers would arrange themselves in a particular pattern, right? And by basically doing lots and lots of numerical examples, Candelas and his students at the time discovered that actually, if you took a particular Calabi-Yau manifold, computed all its Betti numbers, you get a diamond structure in Betti numbers, right? So, okay, this dimension here is now a complex dimension, real dimensions. So the Betti numbers form this kind of diamond depending on what 0, 0, 0, 1, etc. So it turned out that again, just by studying lots and lots of examples, right? This was back in the day where Mathematica was just emerging, so they had to calculate all of these things with lots of difficulty numerically. So they plotted the diamonds, right? These are called watch diamonds. And they discovered that for a particular Calabi-Yau manifold, now I should be clear here, for a manifold to be Calabi-Yau is a very stringent potential economy. It's very hard to find Calabi-Yau manifolds. Yeah. So they said, given a particular Calabi-Yau manifold, I go ahead and I calculate the watch diamond. Right? If I take this watch diamond and I flip it about the horizontal axis and the vertical axis on the diamond, I get another set of watch numbers of these Betti numbers, right? And those correspond to another Calabi-Yau manifold. So to every Calabi-Yau manifold, there's another Calabi-Yau manifold called the mirror manifold. So this mirror symmetry in differential geometry was discovered by these basically trying to do particle physics with these types of spaces. And there's a beautiful story recounted in Brian Greene's book, The Elegant Universe, toward the end of the book, where he said that actually then they discovered that this was a problem. There's an equivalent problem in mathematics that boils down to essentially sphere packing. So the question is, how many spheres can you pack in a certain space of a certain dimension? In an optimal way, right? So mathematicians have been studying this problem for a while and had really only managed to calculate it for a very small number of spaces. But you could pose that sphere packing problem in terms of these Calabi-Yau manifolds, and then the mirror problem became something that you could map this sphere packing problem into. And these guys managed to calculate it. So I can't remember the numbers exactly. We'll check this out, but mathematicians had calculated this up to like n equals 7 or 8 or something, mostly by doing that analytically. But phrased in terms of these Betti numbers and the Hodge diamond, suddenly these guys were able to get like answers for n equals 1,708 or something like that, up to. And then there were several conferences organized in the late 1980s, testing these projections. And there was, there were these epic races in computation between the physicists and the mathematician. The first time this week, this won the competition. So it's a beautiful story, and it would have been a beautiful story even if mathematicians had won. But I recommend following this up a little later. But it's the moral of the story is that, there's a lot to be learned from the structure encoded in these topological covariance. It goes well beyond anything I have to say in this course. However, what I do want to do is show you how to calculate some of these homology groups. Now, there's a lot that you can actually calculate, and if you want to go into some of the detail of this, Nakahara has a lot that he calculates. I'm going to do a couple of those examples. Some of them come from Nakahara, and some of them will come from Frankel. Anyone care for this? And some of them will be just intuitively here. But if you want formal calculation of the homology groups, then ask me and I'll take this. Okay. So our go-to example is the two-sphere. So let's calculate the homology group. And I'll do the two-sphere with the technical triangulate. You're on the picture of this before. One, two, two, three, four. Edges and this is oriented. The oriented special complex. So I'm going to start by computing the zero homology group. So technically, I'm computing it for this triangulation, but given my point that I just hopped on about the homology group being independent of tessellation, I'm just going to call this H naught of F2. Yeah. So to this end, I would like you to note that any vertex is homologous to any other vertex because they both lie at the ends of edges. Okay, they're the boundaries of edges. So, first point to note is that Pi minus Pj, the Pj minus Pi is the boundary of P by Pj. Or in other words, any vertex is homologous to any other vertex. Okay, that's how I calculate. That's how I calculate the boundaries of edges. Moreover, all of the two complex, all of these PIPJs are elements of C1. Right. So they're all edges. You also know that the boundary of any somebody put that up. Boundary of any vertex is 0. Okay. So again, any vertex is homologous to, we're trying to calculate the homology group corresponding to 0. So this is what vertex. Any vertex is homologous to any other vertex. This and all of these guys are one chains. So this is boundary, and all vertices are boundless. Okay. So DPI is 0 for all I as well. This tells me that H naught of S2 is one dimensional. One dimensional. And I'm going to take the prototype for one dimensional space to be the reals. And so I will write H naught of S2 over R as R. Okay. I'd like you to keep this in mind. Had I chosen H naught of S2 with respect to Z, which would have been Z as well. Okay. But I want you to keep in mind the story. And in particular, the dimension of H naught is 1. What about H1? Okay. H1, to find out H1, we first need to find out what Z1 is. Any one chain on the tetrahedron, that we drew there, will only be a one cycle if the vertex that we start on is the same as the vertex that we end on. Okay, so I've got to go, for example, P1, P4, P2, P1 is a cycle. Okay, so any one chain on tetrahedron is a one cycle if the start and end go to see the same. So with this in mind, I can find the following for one cycle. So let's say Z1, and I'll take Z1 to be P2, P3. All right, so that's the edge P2, P3 plus P3, P4 plus P4. So P2, P3, P3, P4, P4, P3. Then similarly, you can show that Z2 is P1, P4 plus P4, P2 plus P2, P1 is a cycle, is a one cycle. And Z3 as P1, P4 plus P4, P3 plus P3, P1 in one cycle, and Z4 equal to P1, P, P, P2, P2, P1 is a one cycle. Okay. The thing to notice about all of these one cycles is two things. One, each one of them, P2, P3, P4 plus P4, P2, is the boundary of a face. Okay, this is true for all of them. So each of these guys is the boundary of a face, and only 3 of these are linearly independent. Okay, so there are 3 linearly independent ones. And their span is Z1. So I can use them as basis elements for Z. Otherwise, Z1 is going to be the set of linear combinations of 3 of these guys. Because there are, and you can check explicitly that only 3 of these 4 are linear. So these are all one cycles, any 3 of which are linearly independent. This tells me that the dimension of H1 of S2 is 3. Because each of these guys is the boundary of one of the faces. So what I mean here is that every element, since each is the boundary of a face simplex of this tetrahedron that Z1 every element of Z1 is homologous to the 0 vector. In other words, one of S2 consists of the 0 vector and partly. So should there be the division from S2 is one then? No. Yeah, it was just no, it's just yeah. So dimensional Z1 is 3, and it's dimensional moment. E1 yeah.
Z1 S squared, not H1 S squared.
Yeah.
That makes sense. So it's same dimension as Z1. Then that makes sense, then same dimension of the B1 with this, it's just.
Yeah.
That's right.
Good. Okay. And then finally, we need to calculate H2 of S2. And calculate H2 of S2. Note that any two cycle is a multiple of let's say W. W is P2, P4 minus P1, P4 plus P1, 2, 4 minus P1, 2, 3, which is the entire subgroup of the two sphere. H2 of F2 is generated by the two sphere itself, and on the boundary of a D simplex because the sphere in a fall, and so H2 of S2 is this R. Let me do one more example. One dimension down. And then we will draw conclusions, one conclusion in particular. And for this, I want to consider the simplification complex for K to be P0, P1, P2, P01, P12, P1, 2, okay, so you can see that this is the complex is a triangle. P0, P1, 2. Oriented triangle. I've already been fine here. I'm trying to do this. So there's no interior. And yeah, this is the triangulation of this one. Okay. So there are no two simplexes in a triangulation. The no two simplexes in this complex means that P1 of K is 0. And H1 of K is Z1 of K on B1 of K is just Z1 of K. So now we can look at what Z1 of K is. So suppose I write Z as, let's say, some I P naught P1 plus a P1 P2 plus a P2 P naught. And I'm going to take for this example ij k to be in Z. And I want this guy to be a cycle. Question is, what are the constraints on ij and k that make this a cycle? Yeah. So when is Z an element of Z1? Okay. You're not going to calculate what dz is. Boundary is this. So dz I think I need d1 is I p1 minus I p sorry, I p1 minus I p0 plus j p1 minus j p2 plus k p0 minus k p2. Okay, by our construction of what? Of how to construct boundaries.
It's not, is j not positive?
JP2. No, why should we go to it?
Going in that direction.
Huh?
Magnitude you suppose you order.
Oh, right. How would we come to this? P1 minus P0, P2 minus P1 in the side, right side. And that would be P0 minus P2. Good. Okay, so this is I minus J P1 plus J minus K P2 plus K minus R P0. And I want this guy to vanish. And it vanishes if I, J, and K are the same. That constrains what I, J, and K are, which tells me that Z1 of K is the set of things that look like I times P naught P1 plus P1 P2 plus P2 P naught with I and Z, which is yeah.
The relation between the homology group of space and the fundamental group of space, because they look fairly somewhat similar.
Yeah. Yes. So homology is counting holes in space, and fundamental group counts essentially paths that you can't deform through holes. So for one-dimensional holes, that's the same thing. Right? For if you take a surface, right? So on a two-dimensional manifold, the hole in that manifold is counted by homology, and the homology also counts the same hole, okay, by paths. Homology, on the other hand, counts higher dimensional holes. So P there corresponds to the dimension of the whole period that the homology is counting. So homology, so for example, if you take three-dimensional space, okay. So if I take a plane and I puncture the plane at the origin, okay, then there are two distinct classes of infinite number of them, depending on the winding, right? But either paths wrap origin or they don't wrap origin. Okay. If I take R3, for example, and I remove the origin from R3, and then I insist on counting paths that I can deform to 0. Right? I can always move the part off and contract it to 0. But there's clearly a hole in R3.
Yeah, but that's why you take a two-dimensional part.
Correct. That's not by the one.
But it's also covered by the second fundamental.
Correct. Right? So you can go to higher homotopy groups, or you can go to higher homology groups.
But are those still the higher homology groups?
No, then they start getting, then the relation gets a little bit more complicated. Yeah. But that's a good observation. If I had another semester, I would tell you about homotopy. And the relation would come on. Actually, if I had another semester, I'd tell you what.
Why is that relevant?
Because I'm on sabbatical. No, I'm not a little time ago. But they won't give me a course if I have some conditions. I already have 12 courses. Okay, so let's see. Okay, so we've calculated then. So from this, it's telling us that H1 of K must be Z. Okay. What about H0? To calculate H0, I'm going to need to use something called the fundamental theorem of homomorphism. Which says that if I've got a map F that takes me between two groups, G1 and G2, and it's a homomorphism. Then G1 modeled out by the kernel of F. Kernel of F is a set of all things in G1 that get mapped to the origin of G2. And that's the image of F. Okay. So what has it got to do with calculating H0? Well, to calculate H0, I have to calculate what Z0 is and what B0 is. So Z0 is the same as C0. Why? Because the boundary of all vertices vanish. Okay. So all vertices have no boundaries, and therefore the set of all vertices is the same as the set of all zero times. And B0 is the set of objects that look like this. So B0 okay, is one of, let's say, L E naught P1 plus M P1 P2 plus N P2 P0. Again with L, M, and N. To do is set of objects L minus L minus L N minus L equals plus L minus N P1 plus M minus N two. With L, M, and N, and Z. So if we define, so we need an S, right? Use that fundamental theorem. So if we define the subjective polymorphism F that takes I E1 plus J E1 plus K E2 to I plus J plus K into the I J K into this. Then the kernel of F is F inverse of 0. And that's just BK. B not K. So what this means is that Z naught of K mod B naught of K is Z naught of K mod kernel of S. And the kernel of S, so Z naught on the kernel of S is just the image of F, the image of F is there. Okay. So that establishes then that H naught of K Z is Z. In particular, since this is independent of the triangulation, and this is the triangulation of S1, says that H naught of S1 is Z, and the dimension of H naught of S and then of S is 1. This is what I want to focus on. Let's say let me give it as an exercise to you. So that H2 of Z, H2 of K then is also Z. Point I want you to take away though is that in both these cases, the dimension of H naught was 1. Right? In both the examples that we looked at. And in fact, this is a more general statement. I'm not going to prove what I have. To nice proof of it. The dimension of H naught of the manifold counts the number of disconnected components of the manifold. Okay. So if M is a union of two pieces, for example, then the dimension of H naught would be 2. If I have a smooth manifold, and it can have holes in it, but as long as the manifold is not disconnected, in other words, going back to your homology example, if there's a hole in the space, then even though I can connect, even though some paths I can't contract to 0, if they wind around that hole, I can always join with a path any 2 points of that manifold. The manifold is connected. Okay, so in that case as well, the dimension of each of them will come out to you. So the dimension of each of them counts the number of connected pieces of the manifold for our purposes, but more generally, it counts the number of disconnected pieces in the solution complex. And the solution complex can consist of many disconnected pieces. So, for example, if you're doing computational topology and you're looking at a solution complex that you made out of a large number of data points, one of the PhD students in our group is using topological data analysis to analyze a set of astronomical objects called fault radio bursts. Basically, there you have something that happens in the sky, and you get some data from this thing that happens in the sky, a whole bunch of data, and each of those data points can be thought of as a point in a multi-dimensional space. And usually it's a high-dimensional space because there's a lot of different parameters for the data. And it turns out that you can take all of these points and you can plot them in the space. And what data analysts normally do is they look for patterns, and they look for patterns by how these points start. But if you use what's called topological data analysis, which actually is a branch of computational topology called persistent homology theory, then you study the shape of that data in the data space. So there you could have clusters that are clustered down here, and then completely disconnected clusters down there. In which case, the dimension of H naught of M, M being the space of the data points, is there no longer just one, because they are disconnected components. Okay. But again, by studying the whole high-dimensional analogs of folds, high-dimensional pieces, you can learn a lot about the data. One of the nicest examples of this in the field of topological data analysis, in fact, came from one of the originators of the field, a guy called Mr. Carlson, where they were studying cancer data, and using quality, they were able to discover a new form of cancer. It's a really interesting story, actually. If you care to hear about it, I gave a TED talk a couple of years ago. If you find it online, I talk specifically about that cancer diagnosis. Basically, there's a really malignant form of breast cancer, and everybody that has that generally kind of dies from it, or they have to have mastectomies or something really drastic. And what people found was that in and amongst the set of survivors, there were a bunch of people that if they just left them alone, the cancer would have gone away. And they didn't really understand what was happening, because if you look at the set of data points, they were kind of aligned in this line, basically, and everything along this line was super malignant, except for like a bunch of little points around the center of the line. Using topological data analysis, Carlson and some collaborators found that actually the structure of the data was not just this line; it was like a T. But if you just look at cluster analysis, you look at a entire layer of a T. But all of the data points that lie on that T, on the long leg of the T, are in and amongst this super malignant set. Benign, completely benign. They go work by themselves, right? But if you go to if you had these symptoms and you went to an oncologist, they'd see the data point sitting here, and then immediately start treating it super aggressively. But actually, it wasn't sitting here; it was sitting somewhere down there, and it took pathologists to realize. Anyway, on Monday, I'm going to use the Euler character, which probably everybody knows, but we will generalize the Euler character, and I'll show you where this B minus E sub F comes from. Yeah. And would that be F1 or the same? No, it's
Very